Okay, so today we're going to talk about section 8.1 and a little bit from section 1.6 that we skipped a while ago. So our essential question today is, how do you find the sum of the measures of the interior angles of a convex polygon? Anytime that you guys need to pause this, go ahead and pause so that you can copy this down and set up your Cornell notes. Topic is section 8.1, EQ, and then don't forget to put the date as well at the top. Some of you are missing that easy point in your heading because you weren't doing those when I checked your C notes. Alright, so one main idea today is polygons, and our first is definition. A polygon is a closed figure with the following properties. So closed just means that all of the ends touch each other. There's no gaps or openings. First, it has to be formed by 3 or more segments, and we call these sides. So 3 or more segments. Can't have 2 segments because that would not be a closed figure if you made 2 segments. So it is formed by 3 or more segments that we call sides. And each side intersects exactly 2 sides, one at each endpoint. So in a moment we'll do some examples so that you can see what this means. Our next vocabulary term is a regular polygon. A regular polygon is a polygon with all congruent sides and all congruent angles. So for instance, if I were to draw an equilateral triangle, that is a regular polygon because all 3 sides are congruent to each other, and remember, in an equilateral triangle all 3 angles were congruent to each other. So our equilateral triangle is a regular polygon because all the sides are congruent to each other and all of the interior angles are congruent to each other. And then our next vocabulary term is diagonal of a polygon. And what a diagonal is a segment that connects 2 vertices that are not already connected. For instance, if I had this square and I drew in the 2 segment, or if I can get my pen to change here. So if I pick this vertex is not connected to this vertex. So if I connect those, that creates what we call a diagonal. I could also connect this one with this one and make another diagonal, so this square has exactly 2 diagonals. These 2 points are already connected, these 2 points are already connected, so on and so forth. So that is a diagonal. Alright, so example 1, go ahead and glue the example 1 into your notes. If you need to pause, you can do that. Alright, so in example 1, it's asking us which of the following is a polygon. And remember our definition of polygon earlier, it has to be a closed figure. It's formed by 3 or more segments called sides, and each side intersects exactly 2 sides, one at each endpoint. So if I look at this first one, letter A, is letter A polygon? Well, I'm hoping that you say no, because letter A has a curve. And so this is not a polygon. Polygons are not made up of curves, they're only made up of segments. So that is not. Okay, if we look at B, B is a closed figure, and they're all made up of segments, so that part. But if you look at the second part of the definition, if I were to pick this segment right here, that segment. Well, remember in the definition it says each side intersects exactly 2 sides, one at each endpoint. Well, if I go back to the picture, this segment is connected to this segment. It's also touching this segment. It's also touching this segment, and it's also touching this segment. So this is not a polygon because this segment is touching at its endpoints more than just 2 other segments. So that one's out also. C has all segments, no curves. Also, if I pick any segment that I pick, so if I pick this segment here, this segment is connected to only 2 segments, this one and this one. Same here, if I drew this segment, it's connected by this one and this one. This segment is only connected to this one, and so on and so forth for every single segment. So C is the polygon. And if you want to write in your notes why the other ones are not, you can, to make sure that you understand. Okay? Now there's two types of polygons. Once you've decided that a figure is a polygon, then we have convex polygons and concave polygons. So pause for a minute and go ahead and draw these in to the best of your ability, sketch those in, and then we're going to kind of see if we can decide on our own definitions of what it means. All right, so now that you've copied these, notice that convex polygons look like this, concave are like this. So maybe you might be thinking, well, convex looks like it's all of the vertices are pointing outwards. So all of these vertices are pointing outwards, all those are pointing outwards. Whereas maybe one or more of these vertices is pointing inwards into the polygon. Same here. This one's pointing in and the rest are pointing out. This one's pointing in and the rest of them are pointing out. So that's maybe one way that you want to think of these. It's not like a formal definition. I'll never ask you for a formal definition, but I may give you a picture or a bunch of pictures and I may ask you which of these is a convex polygon. Or I might ask you which of these is a concave polygon. You have to be able to know the difference between the two. Okay. Now the technical definition says that if I draw all of the diagonals in each figure, all of the diagonals lie inside. So for instance, if I drew in all the diagonals in this, we would have this. So that's all the diagonals drawn in. Notice every single diagonal lies within the original polygon. Whereas here, if I draw in all of these diagonals, I would have one there and I would have the one there. This one is outside of the original polygon. So this one's concave because one or more of the diagonals fall outside. That's the technical definition. All right, so you'll need to take a moment, copy these down. This is vocabulary that you're going to need to know. So three-sided figures are called triangles. Four-sided figures are called quadrilaterals. Now you may be thinking, well, a square and a rectangle, those are four-sided figures. Yes, those are special types of quadrilaterals, but just all four-sided figures in general are called quadrilaterals. That quad part means four. 5 is pentagon, 6 sides is a hexagon, 7 sides a heptagon, 8 sides octagon, 9 sides nonagon, 10 sides decagon, 12 sides dodecagon, and after 12 we don't get very creative. So a 13-sided figure is going to be called a 13gon for 13 sides. If it had 100 sides, it would be called 100gon, the number 100 - gon. Now you may be asking, what is an 11-sided figure called? There is a name for it, and I'm going to make that extra credit. If you can look that up and find it and put it at the top of your homework tonight, that'll get you an extra credit point. Maybe see if you can guess what it is first, and then see if you're right. Okay, so if you need to pause so you can copy that, go ahead. Okay, so now let's look at this square. There's some fun things that happen inside polygons. Okay, so let's say I pick one vertex and I draw in all the diagonals from that one vertex. So I'm going to pick this vertex and I'm just going to only draw in the diagonals from that point, and there's only one. Now notice I just made two triangles. Okay, what do we know if I just looked at one triangle? What do we know about the three angles inside a triangle? I hope you're saying they add up to 180. So this triangle adds up to 180 degrees. Same with this triangle. If I added this plus this plus this, that would also add up to 180 degrees. So how many degrees do you think, if I took away the diagonal, how many degrees total do you think that this triangle has? Or I'm sorry, that this square has? Well, hopefully you're doing 180 plus 180, which is 360. So actually what that means is that inside every four-sided figure, the four angles, this angle plus this angle plus this whole angle plus this angle, is going to add up to 360 degrees. So if I were to take away this segment, so if I were to take away all this work we just did and just had this quadrilateral, what we know is that any four-sided figure, if you add up the four angles, it adds up to 360. Okay, because remember in a triangle, if I add up the three angles in a triangle, they add up to 180. Any kind of triangle it is. Okay, now let's look at a hexagon. This is a six-sided figure, a hexagon. Let's say again I pick one point, one vertex, and I draw on in all the diagonals from that one. So that's one, and that's one. Okay, how many triangles do you see here? There's four. Each triangle is 180 degrees. So if I did 180 times 4, that comes out to be 720 degrees. Which means, if I got rid of all those triangles, what that 720 degrees means is that if I added all 6 angles inside any hexagon, any convex hexagon, not hexagon, hexagon, then it adds up to be 720 degrees. Whether these are all equal to each other or they are all different measures, inside every six-sided figure, there are 6 angles, and those angles will always add up to be 720 degrees. Now, we don't want you to have to do that every single time, where you draw the picture, and then you draw in the triangles, and then you add 180 times however many triangles there are, and get your answer. Okay, so like here, we would have done 180 times 2 to get our 360. We don't want to do that every time. So there is a shortcut formula, so I wanted to show you this first so that you could see where the formula comes from. So the formula is, if you ever want to find the sum of the interior angles of a convex polygon, so remember convex, not concave, sum of the interior angles of a convex polygon, that's going to equal 180, because notice in both of these we're seeing how many triangles there were, so 180 times n, where n is the number of sides, minus 2 in parentheses. So let's look at that. So in this one, n equals 4. Because there's 4 sides. So n is the number of sides. So if I plugged in 4 minus 2, that's where this 2 came from. Because this n minus 2 represents the number of triangles that is inside the figure. Okay? And if I plugged in, this is 6 sides. So hexagon has 6 sides, so n equals 6. So if I did 6 minus 2, I get 4, which is where this number came from, and then you multiply it by 180 degrees, because that means there's 4 triangles. When I drew those in, there were 4 triangles, and I multiplied by 180, and that gives you the sum of the interior angles of a convex polygon. So if I wanted to know how many degrees are in a pentagon, so pentagon is a 5-sided figure, so I would do 180 in parentheses 5 minus 2, and that would tell me how many degrees the 5 angles in a pentagon would add up to equal. So we'll do some examples over how you're going to use that information here shortly. Okay. All right, so about time on this video, so then you're going to go ahead and start video number 2.